We're going to find the Lagrange error bound in approximating natural log of 1 plus x at 0.6 using the Maclaurin polynomial of degree of 3. First of all, the Lagrange error bound sets a maximum on how far away your approximation is from the actual value. So it's a good thing to have. So first of all, let's talk about what the Lagrange error bound is, and it's this. It's R of n because it's the remainder. It's what the actual value is minus your approximation with the Taylor polynomial. So if you subtract them, that's called the remainder. And the remainder is not going to be any more than this function you see, or this value you see right here. So it's a pretty straightforward formula, even though it doesn't look it. It's just really the next omitted term in creating a Taylor polynomial. So it's very similar. The only big difference I can see here is this z. What is that z? So first of all, before we look at that, this is a Maclaurin polynomial. So really, that means it's a Taylor polynomial whose center is 0. So let's call C 0. X is where we're approximating. So x equals 0.6. So z, this z right here, z is any number between C, the centering point, and x, the point that you're evaluating the function at. So here we go. If we're going to use the third degree Taylor series or Maclaurin, we need to, for the Lagrange error, we need to get to the n would be 3, so we need to get to the fourth derivative, and 4 plus 1 down here. So you can kind of see that. Wasn't very well explained there, but you can see that. So all I know is I'm going to need the fourth derivative of this function. So I already did that for you right here. The fourth derivative of this function is -6 over 1 plus x quantity to the fourth. So now that we know what everything is, we're going to use this error bound formula to figure out how far off our approximation could be with a third degree polynomial. So the maximum of the difference could be, the remainder, is the maximum value of the absolute value of the fourth derivative at any value between 0 and 0.6 over 4 factorial times x minus c. We set up there x is 0.6, c is 0 to the fourth. Now this is also an absolute value. So if it's negative, you just make it positive. It's just the difference between them. So let's talk about the maximum value of the derivative. Here's the derivative. We're trying to figure out where that's maximum between 0 and 0.6. Well, we know enough about, and it is also the absolute value, so you can ignore this negative. We know that the bigger the denominator of a fraction gets, the smaller the value gets. In other words, 1 over 10 is much smaller than 1 over 2. So if I had to choose between 1 over 2 and 1 over 10, I would choose 1 over 2 for the maximum. So if you're plugging in 0 to 0.6 in the denominator, you can see the denominator is getting bigger as you get higher than 0. Therefore, the fraction itself is getting smaller. We want the maximum value of this fraction. So that's going to happen when x is 0. So there you go. That's what the maximum value of this derivative is going to be between the centering point and the value of x that we're approximating. So we can just do this now. 6 over 4 factorial times 0.6 to the fourth. And now we're going to let our calculator do its magic. 6 divided by 24 times 0.6 to the fourth. I'm getting the Lagrange error bound, or the maximum our approximation could be off, is 0.0324. So we know that when we approximate the actual value of the function at 1.6, or at 0.6, minus our polynomial at 0.6 is not going to be any greater than 0.0324. And that's how you use a Lagrange error bound. That's all there is to it.